working and how magical it is. So I have divided my talks into parts only because of the fact that, as you can expect, that I'm on tenure track still. And the new data always excites me because there was a couple of years I was giving some talk about my postdoctoral work and I was never happy. And now I'm so excited because I have a lot of data and I see that people hear about superconductivity. So I will talk about some magic angle samples. And I will also talk about some magnetic field induced superconductivity because I see a lot of overlap here. So that's the reason. So with that, I will start. So the reason for me to move to flat bands and not do just Landau level physics because there are constraints. So the reason what inspired us is that there is, I mean, I'm sure you guys have seen this a lot of time. If you twist graphene on graphene, you will get a flat band, just like Landau levels we are used to, maybe not as flat as that, but yet flat enough to basically quench the kinetic energy and give away a lot of phases of matter that is just really so thrilling to have under the same roof. So basically, we are quenching the Fermi velocity and we are having flat bands where electrons are showing up in different states. And the first work was done in 2018, and since then a lot has been evolved. But just to show you that the things that has been already recorded in this system was superconductivity, ferromagnetism, anomalous Hall effect, Bowman-Chook effect, you name it, they have it. And hence we were very interested in deployment into this system. But those of you who are aware of twisted bilayer, you know that the ohmic contact to these samples are not easy. So that's the reason what I did is like I moved to twisted trilayer graphene because of two reasons. Now you have a complicated system because you have to twist 3 layers of graphene. Control is even less. Understand that human beings like us are making the sample, so it will be full of disorder. So getting a very good sample is thanks to a good student. Anyway, here also you have flat bands, but along with that you have Dirac. So that helps you to get good ohmic contact and easier for us because even if you have a Hilton-3 system in your lab that works, you can see superconductivity. So that was our motivation to delve into why we choose TTG, but maybe not only just that, but TTG has shown more versatile phase diagram given that now you can also change both the gates and you have a displacement field or electric field dependence on your phase diagram. As you know, we physicists would like to control our electrons as much as we can. So one more knob is better than none or two. So there is a robust superconductivity there, and somehow the angle is not as accurately has to be magic angle. This is a bit flexible than that, I would say. And the superconductivity or correlated states, something that you guys have definitely bumped on in one of your conferences. So I'm not going to go into details, but what motivated us, a few results just before I started, is that in parallel magnetic field there are reentrant superconducting state that has been seen in UT2 or something like that. So it's kind of rare. Then there is superconducting diode state, which was also kind of seen here and it's kind of rare. And then there are also kind of other stuff where there are superconductivity and pneumaticity, etc., that has been seen. So we understood that this has a one more knob and maybe temperature is a bit higher for us. And we started working into this, knowing that it's a versatile platform, but just so already when we were entering this field, the superconductivity was known for its unconventional nature. There was some strange metal behavior, nodal gap measurements. Then there are pseudo gap measurements, pneumaticity. Again, you name it, they have it. And hence we thought that still the order parameter is not known. Not that I'm telling you that with transport I can solve the problem, but the relation between the correlated states and the superconductor was still unknown. And one more knob with the displacement field could have been helpful. And the role of electron-phonon interaction when we started, still now people are not so sure, maybe. So these were the still open questions, and I will talk about more open questions in the panel discussion in this field. So with that, we go and we make our sample. don't have to go into these details of the 2D plot. It's just to show you the quality of the device. It's a very good quality device. And how do you know that? When you see your insulating state is really not very wide but very narrow in density. That means it's a very good quality sample. Anyway, so this agrees well with the previous data. So what did we add in the literature, if at all? So what we found out that this superconducting state that we have here and also in the electron side, graphene, I must tell you that not always is symmetric, like the results are not in electron and phonon are symmetric when we talk about superconductivity. So what we found is that superconducting state in both cases, but the moment we started looking into the temperature dependence, I know you may have to be a bit kind towards my data, but there is kind of double dome feature there in the superconducting state. So this dome is not just a single dome, but then there is some suppression of this PC, and then it goes up again. So this was, by the way, before us in STM measurement from Caltech, there was U to V transition. They showed in their gap, and this was the first time in the transport we would see because of the high quality sample. So this is the thing, that there is a suppression of superconductivity near nu equals to 2.6. Why that? But it keeps coming on every sample, so I don't know. And the thing is that the linear behavior, if you look at the RT, it's somehow there is some difference that tells you that this one is a bit weird, which is also known as a bit modal in nature in terms of superconductivity. And the right dome kind of looks normal superconductor as you'd expect. So what did we do in order to kind of prove that we use the double dome? We put some magnetic field, and as you can see that here also we can see double dome effect. So just,
out of play.
Sorry?
Is it in play or out of play?
Out of play.
Out of play.
Yeah. Yeah, I wish I could put some in too. Okay, so the thing is that you can see indeed that there are two lobes of superconductivity, which is not very simple, but you can see that one basically stems from the insulating state at -2, and the other one is stemming from insulating state at -3. We would like to believe that these two are different in origin, and I would just show you a few more data, because as experimenters, that's what we do, like keep showing data after data. I don't know why it doesn't work, maybe I'm too far. Okay, so let's see also the current bias, because does it really show some kind of suppression here? It does. And then there is this normal hysteresis that you will expect from the heating effect. So we do see double dome in every kind of signature that we look for. And this, of course, we wanted to understand why we are seeing double dome. And so, as I said, there is also displacement field that we have. So we also wanted to know whether this is really uniformly all over. We saw no, there is a very small window of displacement field where we see this double dome. And with all this information, we definitely wanted to go to a theorist, where all I can tell you that as you go from displacement field small to high, what happens is that if you can see here, there are these Landau levels. Remember I said that twisted trilayer graphene will also have Dirac electrons. So we have flat bands and we have the Dirac electrons. So we have these Landau levels from them. Slowly, as you can see here, the Landau levels are not as visible as you would like. Here it is none. So here the hybridization of the Dirac and Landau, the flat bands are complete. You are back in the single dome, while in between where they were competing with each other, we see this double dome, basically. So they said, give me 5 minutes before you tell me. Okay, so the thing is that we collaborated with theorists, because we know that in order to understand for us, we were given that field at the time. And my collaborators from Oxford, they have done this Hartree calculation, and they indeed see that there is a wedge exists, which basically tells us that, I mean, I'm sure in the audience there are better theorists than me, so I'm not going into the more details of the theory, but the possible superconducting pairing states in the two domes are basically. The right dome basically means pairing between electron with the same and opposite effective spins, but the left dome is kind of only same effective spins. That is what we claim in our paper.
What means effective here?
Okay. I'll step back, yes.
What is effective?
Because of the fact that, sorry, you see there are this U and L, we have both. So I think you can tell me better, you are a theorist. These calculations that, effectively if you take the two doses and you see that effectively the spins can be up and down. But if you want to be on the left dome, you really have to have all the effective spins are in that direction.
You don't know what is effective.
Okay, yes, because I'm not a theorist, I will not go into the details and make a fool of myself. I'll show you the reference. Thank you. So, yes. So the conclusion of the double dome part is that this has been seen in different other materials and kind of curious. It's not so straightforward. We don't see double dome in everyday materials, and hence I would like to say that another member of the double dome superconductivity. Here, I would like to say I'm no way telling you that I'm going to solve any high temperature superconductor problem, or I'm not even drawing any analogy to it. I'm just saying it also showing the similar behavior as those. And then it shares the same or the different order parameter. We don't know. As I said, we tried doing some corner squeak stuff. We are still not successful. If we could do it, it would be great. And then why does this double dome superconductivity appears in a small displacement field window? This is something that we still don't know. Okay. With this, I would like to. Okay, so the displacement field is definitely doing something in the MATTG, like magic angle twisted trilayer graphene, which was completely absent in bilayer graphene. So the double dome superconductivity only exists in small displacement field window, and the most direct consequence of the displacement field is band structure change. So we believe that there is a hybridization of Dirac band and the flat band. The definitely change of flat band width because of interaction. And also the last thing is the other effect by the displacement field, which we don't know. So that's maybe is the thing that it is definitely doing. This is a part of the, so what we did is like, this is the full ND map of this magic angle twisted trilayer graphene. As you can see that this is, symmetric around displacement field 0. And what I'm not going to go to the details because I was afraid that I would not be able to then show you our new data. So this robust superconductivity actually exists in both hole and electron side in our sample. And the correlated states and the superconductivity can be tuned by the displacement field. And what I can show you is that exactly what I was trying to say is that if you have in the only right dome you have a very small displacement field, so you have just one dome. But whenever you go to a middle, moderate displacement field, you start seeing this double dome where you have hybridization between the Dirac and the flat bands. And then again, if you go fully, again, completely hybridized Dirac and flat band, just gives you one dome back. Superconductivity is tuned by the displacement field, and the domes only are in the intermediate window that we have proved. And this was been published last year in Nature Physics. And there you can find the theory in details. Now I want to show you that, so this is our critical conclusion that there are some critical fields that is basically appearing in our data that in somewhere like there is a Litvis transition there, then there is a Hall density that is changing, which data I'm not showing. If any of you are interested, I will show you later, but definitely we think that there is some kind of connection between them that can help us to get rid of this riddle. But what I want to now go later is that what happens when the angles are different. Remember, we are talking about magic angle TPG. That means the two layers of graphene were twisted, and then the third layer was twisted back. So alternate angle I have. Now the idea is that what if this 2 theta is not same? Will I lose this double dome feature, or will I even lose the entire superconducting state, etc. So again, we are not the first here. Other people were already working with the TEM and STM, showed that there are supermorae. And you can see also this paper. So interference of the two morae lattices gives you supermorae. And our idea was like, how does this tune the phase diagram? So as you can see here, that it is not really symmetric around d equals to 0. Here and here, they are similar, but not here and here. So we can directly see that there is another effect there. There is an isotropy in between the two sides of the D. It's asymmetric, and superconducting states are still happening. As I said, it's very, very robust. In fact, the superconducting diode effect, though we didn't see in our device, has been actually found in one such devices. So two twist angles are different. That is what we wanted to make, and it's a uniform device. Let me just show you again, just to tell you that this device was a very high quality and uniform. And the theta we just simply measured from the two morae, and then there is this Brown-Zach oscillation. Namely, you just ruin the superconductivity, and then you go to a higher temperature, and from their oscillation you can find out the other morae in the system. So that's how we calculated. And then we found out that our calculation from the Landau levels and also from these are similar. And these are some details of our analysis. I forgot to hide this slide because I didn't want to go over all this stuff. Let me just show you. So there is also interactions. We saw a lot of in between states that are showing that we still have interaction between isospin broken states. And finally, coming back to the superconductor. So I showed you between filling factor 2 and 3, there was 2 superconducting domes, and this is something not that happens in every superconductivity. But now, as you can see, that there was one dome that has been sliced by the mini bands, because now we have the other morae. So the supermorae basically doesn't really kill the superconducting state. What it does, it just slices into small bands. So as I said initially in my talk, that indeed the superconductivity in twisted trilayer is pretty strong, and it has more parameters, so it should be understood. It's pretty interesting, and all I can say that there are 2 pictures for the AC transition that we can think of, and this is something that long ago we discussed with Yuval, that then we drew this by hand, that there can be interaction that is more than the supermorae gap, or there can be interaction that is less than the supermorae gap, and we see this dicing of the superconducting dome. We don't know which one is true, but definitely we favor this one more, that we would like to think that the interaction is stronger than the gap that we are introducing with the supermorae in this case. And this work has been also published earlier this year, so the reference is here. And from now, I would just simply say, I would conclude this part, and I will finish in maybe 10 minutes the new part of the data that we have. So exactly, we see the interference between this. We gave proof that we do have 2 morae lattices, that we have the interference in using our transport data. We also saw isospin symmetry has been broken. Supermorae lattices offer now a new platform to design unexpected electronic quantum space, because you see this is another tuning parameter that you have. So this is our conclusion, that if I combine my twisted trilayer part, that we show that there are gate tunable double dome superconductivity in twisted trilayer magic angle 1. Then there is critical displacement fields in the MATTG, which may uncover why we see this double dome superconductivity. And we also see the existence of supermorae in the mirror symmetry broken DTG. With that, I would want to thank this boy, because without him, nothing will be done, and tons of other collaborators. And you will see his face keep coming again in the next work. So he's pretty good. He's my second PhD student, but yeah. So this is Zikant. Let's move to the new thing that everybody is jumping on rhombohedral graphene, because I really want to do some zero field fractional quantum Hall, like FCI. So the thing is that for those of you who don't know, or maybe know, that there are two kinds of graphene that exist. One is Barnard, which is we are always listening to. And then there is something rhombohedral. There's a paper, I think, which group I forgot, from England, that said that actually ABC is more stable, but it is only found less than 15% in natural graphite. So finding it is a bit difficult, and somehow it relaxes, but thanks to Andrea Young, we now found a better way to get bigger flakes and how to get a stabilized stack made. And then you have students that makes a stack, so you do physics. So I would just show you guys that here also we have some flat bands. It's just that I do not have to engineer. My student now have to find the rhombohedral part of the flake using IR and Raman. And then you basically isolate that part of the flake and make the stack, and you get the data you want. And I will focus on the superconductivity part there. But I would just like to say that there is a zoo of superconductors in this material. Just think of it. It's few layers of carbon starting from 3 until 8 layers. I know that there are. So this is 8 layer. This is 4 and 5 layers. And this is, I think, again, 5 layer, stuff like that. So this is just to give you an idea, like even in carbon, just in the same place, you just tune your displacement field. You are going from chiral superconductivity to triplet superconductivity to whatnot, okay? So it's basically, as I said, we are physicists. We would like to have something that we can control and tune it to our wish. So with this, I would just specifically mention what actually was our motivation into getting into this work, apart from FCI, is that this chiral superconductivity. I know that if there are theorists in this room or they're aware of this work, maybe me telling this term for chiral doesn't make you happy, but that is what is going on. Now it's a magnetic superconductor, you may say. The thing is that this was the first work where, so all tests were done. This is not my data, so I don't want to spend too much time. Just to tell you that this is the reference. You guys can go and watch it. It's a work from MIT, as many other works in this field has been done from MIT. So this is one thing. And what we realized when we were seeing this, yes, I will be very quick, that if you now pay attention to this part where all these FCIs, namely zero magnetic field fractional states, were actually shown, this insulating state, and look at this insulating state, they look pretty similar. And that is what put us in this work when these two papers were on arXiv. So we understood that this is just an overview. The PPT will be given to Claire, so you guys can look at it at your free time. But what made us curious into looking into this insulating state, I know it's not superconductor, but I'm going to that this must be something that is important to look at. And I know that when we were looking at it, there are other people also looking at it. Obviously, they were before us. Our paper will be more in arXiv. So the thing is that there is, because my student doesn't like until it goes to a reviewer, it is on arXiv. So we are not in arXiv. So this is the thing. So chiral superconductor, I'm not spending too much time. All I want to say that indeed this insulating state, you have bias dependence. I'm sure there are many theorists here and they will like to hear something that is Wigner crystal, because, I think I keep that slide because I thought I will not bore you. But basically this state is Wigner crystalline state, okay? But what we are interested in is this, that the moment we increase the magnetic field, here the superconductivity goes down, but here a superconducting pocket comes up and here a superconducting pocket comes up. So let me just show you that. Okay, so region 1 is here superconductor, here what it is I will show you, and here also superconductor I will show you. Rx6 doesn't go to 0. So don't be upset. So the thing is, when I call it superconductor, is I want to say that Rx6 and Rx5 both are going to 0 in these two pockets, and here it is not. You just pay attention. So what we saw is that both chiral superconductivity are basically suppressed. This is the chiral superconductor. And the region 1 shows that two states. So the paper that we have submitted, it's all about having this Wigner crystal to be the parent state of maybe all these states around. That's our idea. And the first part is that the bottom part of our so if we go here, and we would like to, I don't have time, so I will go fast. So here we are taking a Landau pen, and as you can see, the top one doesn't show you any, finite charge, but just blob of low resistance. So this is the superconducting state. And on the other side, we have green-term quantum Hall state. Just to show you the superconducting part is that we tried doing everything, but indeed we could not go to 0 resistance in Rx6. For that, I will suggest you to look into this paper, but they have a new paper submitted in arXiv, I think last week. So they in hexalayer graphene goes to 0. For us in pentalayer graphene, in multiple samples, we could not go to 0, but these are the tests we did. And then just to show you that why we think about this connection between this. So this is a metallic Wigner crystal. So here there is some unpin carriers, which are all in nature in the electron side. And we see that there is a kind of direct connection, if you can imagine that this blob is here, etc. And also they melt in the same time in a way, the superconductor and the Wigner crystal, etc. We tried fitting here, we could not meaningfully. And hence we gave up and we just submitted whatever we had. So I just wanted to show you that, we definitely have this one picture that it can be anomalous metal, which is, by the way, my friend Matt came up with. So his paper is under review, but we'll archive it. So this field is so fast, people don't want to share their ideas unless they're friends. So it's anomalous metal can be a picture. This is something that we talked to Steve Wilson also. I don't know, because now in my lab, so this some data was taken in Weizmann in my previous supervisor's lab, and then because there was some problem in Israel, we could not fly. So this year we came to CEA in Saclay in President Rolu's lab, and we continued those measurements. Anyway, so the thing is that in my lab now we can cool down with a new cold finger, and we can go below 20 millikelvin. We can actually see 0 resistance in many cases. But this device is now in CEA, we are measuring noise, so I didn't repeat. Anyway, so I just want to show you that why I call the region 3. Remember on the top is also like superconductor, because kind of that's what it shows. And this is the one that kept me away from the conference yesterday, because I went there to discuss about how to finish this paper. So we are doing some short noise measurement. I just want to show you that indeed there's two curious things happening, that in this state, of course, I could not show you 0 resistance, but the Fano factor here and here are basically going from 2 to 1. So that is all I can say. This is something that I think Preden should show. It's more relevant than me, because he has spent a couple of years or more to build the setup. But all I can say that here we can actually show that the Fano factor is doubling in the superconducting state. But what is even more curious is that if you pay attention in all the temperatures until almost 700 millikelvin, the graphs are all falling on top of each other, which we don't really understand yet. So we are talking to a theorist. But with that, I would just summarize. I can just go on. Again, you see, that's the guy, and this is my German kid. He keeps the lab in place. They enjoy together working, and as I said, there is short noise measurement now going. And the mantra of our lab is anyone can do, because I also do some quantum Hall graphene. And thank you for your attention and the extra minutes. Yes.
In this short noise data, you showed that there were 2 different parameters on the same thing, which is fitting the Q and the F.
Yes.
What is there?
So, you know,
Because how can you get that E when you have some F that is
so this F, okay, so this is not a junction. This is just the same call bar I was showing you so far. So because we don't have junction, we cannot really know the transmission.
so mine is
here.
bad,
Yeah.
it's
So
best.
what we do is that we go to far place where we know it should be 0.3, let's say, or we normalize it to
assuming
1.
it's diffusive.
Yeah, yeah. And with that, normalizing it to 1, we go and we do the rest of it.
Okay, but if it's not diffusive, then
That you are perfectly, that's why I said, you know, these are ongoing experiments, and I think Brendan could answer the question better because I just took the data yesterday from them. just to share that we have some superconductivity. Or maybe it's on believers. If no other question, let's thank the speaker.